It's always a pleasure to be part of these MediaX events because I think it really brings together a whole variety of folks that we don't normally get to hear in this sort of one environment. And so just to say a couple words about myself, my background is neuroscience. I'm a PhD in neuroscience. I actually have spent most of my time in the defense and intelligence world, so 15 years of that. I'm happy to say I'm emerging and now just advising and not deep into it. But actually, while I was there, I was a program manager at DARPA for 5 years, and we're talking about autonomous cars. We're talking about all this great stuff. It's actually the 10-year anniversary of the Urban Challenge, which is the autonomous car test that happened out in Victorville, California. And for those of you that don't know, all of the program managers were actually all of the judges and the people who worked. So I was there, and I can assure you that in the trolley problem case, the autonomous car probably would have run you over, but there was someone in the car who had an e-stop that would have stopped them. So that's the solution to the problem. But we've been doing this for a long time, and we've been thinking about both autonomy and AI for a long time. And so today I hope to just sort of illuminate some of that from a bit of a neuroscience perspective. So just really quickly, takeaways from the talk. I know they're on the paper in front of you. I think I want to cover why humans need an upgrade, what I mean by human 2.0, sort of the vision of a Centaur, some case studies, how to build one sort of from an architectural perspective, what we might want to think about, and then application domains and their expected impact. Just to cover, this is actually a conversation that Thomas Friedman had with Astro Teller. I have it actually on a napkin because I think it happened at a bar or something like that. So I wanted to sort of capture that in the moment thing. But essentially, technology is going like this, right? And human adaptability is kind of staying flat for Neil, you referred to it this morning, right? That we haven't had an upgrade in the human brain for quite some time. And the problem is not just that we haven't had an upgrade in the human brain for quite some time, but we actually normally rely on technology to give us that upgrade or that edge. And so I think we're in this spot now where technology is not just sort of enhancing us, but it's actually kind of like kicking our butts, right? And so we need to actually do some things that will allow us to sort of upgrade the wetware at the same time as we're sort of incorporating all these new technology pieces. My argument is that, and this may be biased because I'm a neuroscientist, but I do think that some of the things that we're talking about in modern neuroscience are actually going to give us that edge in our wetware. Now, I'm going to give a caveat and say that in the past, I've talked about neuroplasticity. I've talked about how to make elite performers better. I talked about expert teams and group synchrony. I'm not going to talk about any of that today. So if you want to hear about that stuff, please hunt me down afterwards. There's lots of breaks and other sessions, and we can talk about those things. Today, I'm specifically going to talk about the sort of that side of the page where I'm talking about merging brains with technology. I think there's a huge opportunity to upgrade our brains using technology, like the things I've talked about, neuroplasticity and other types of interventions, and I'm happy to talk about those. But today I really want to talk about this sort of enhanced human cognition through this merger. We have a concept at the Platypus Institute called Human 2.0. And when we talk about Human 2.0, what we mean is this really broad picture of all the fantastic things that we can do to ourselves to really kind of upgrade our experience, right? And so the things that we want to be, right, are we want to be adaptable and creative. We want to have increased memory. We want to think intuitively. We want increased processing capacity. These are all things that I believe right now we can actually work on in our human experience through neuroscience. On the other side of the page is actually what I'll call the emerging capabilities, which is like really cool stuff, right? Like, giving ourselves sensory enhancement through maybe the implantation or other types of sensory devices, brains being networked to one another, whether that's through the sort of Internet of Things or actually connected to one another, or actually, the sort of some of the work that you've seen actually recently in the popular literature on increasing memory through both the stimulation of memory systems as well as the uploading and downloading of memories. So when I talk about Human 2.0, I want you to take a big perspective. I want you to think broadly about that, okay? Now we're going to go back in history. And because I was at DARPA during what I call the the cognitive computing or cognitive system sort of re-revolution. We sort of I dug up this, and Licklider. So J.C.R. Licklider was actually one of a really famous guy at DARPA. He coined the term, essentially originally coined the term man-computer symbiosis. And you can sort of read the quote, but the idea that human brains and computing machines will be coupled together very tightly, right, was an idea of his from 1960. And I would argue that we are not quite at this level of human-computer symbiosis yet, but I think we are approaching it very quickly. Right now, I think the investment in this man-computer symbiosis is actually well below where it should be. And I'm going to make the argument for our Centaurs that this is the place that we both need to invest, build, and think about sort of the future implications. So we've heard some great introductions about Centaurs today. I won't go through it in deep detail. We talked about chess. We talked about Go. We've actually, so these expert systems, right, they originally beat the human experts, right? When Garry Kasparov was beat by Deep Blue, that was sort of a big deal, right? Because it was like, oh crap, AI is starting to sort of beat us in things that we didn't think were beatable. We've actually had lunch and had conversations with Garry, and what he said was really interesting, and if you read his new book, Deep Thinking, is that he wasn't actually, although he was upset about losing and he was sort of upset about the conditions under that, right? He was actually excited by the opportunities that it afforded in chess for new ways of playing and new ways of thinking about playing. And so he actually then started using chess engines, and eventually we came to the freestyle chess that I'll talk a little bit more. But the important thing about those Centaurs, right, is that later, you didn't need a grandmaster to team up with an AI or a chess engine to actually start beating computers. And this is where we're at with freestyle chess now. And the reason is that because the combination of the human and the AI was a better combination. Humans are good at the things that humans are good at, right? And machines are good at the things that machines are good at. And the reason is, I think, is because humans are good at seeing patterns, but bad at assessing probabilities, which we actually just sort of heard about from the finance perspective, and especially many moves ahead, right? And so when we think about Centaurs, I want you to sort of, again, relax, think broadly, and think about the places in sort of your work and your domains where this might be useful, and both where humans and computers are good. So we've talked today, we've had some amazing conversations about the biases, right? We've sort of had this list, right? But computers have issues too. We just heard this fantastic presentation from David Bailey about convincing statistics but unreliable conclusions. One of my favorite charts is actually here, the very tight correlation between the divorce rate in Maine and the per capita consumption of margarine. I mean, that's like rock solid right there. But the point is that it is possible to create spurious statistical correlations, right, that have very spurious conclusions, but they're pretty tight. The other thing is, that young boy is holding a baseball bat there. No, he's not. He's actually holding a toothbrush, and we talked about computer vision and other things. One of my colleagues likes to use the example, very simple example, go outside, look out the window, and tell me if it's safe to go outside, right? That's a pretty easy thing for us to do, but a computer vision system does not have that same sense of context and safety that we do. The other thing, we've heard tons today about black boxes and boxes that might have the top open, but they're still blocked. There still are some opaque processes that are going on. Human challenges, I think, fortunately or unfortunately, we're all pretty familiar with these, right? Our own perceptual and cognitive biases. Our reasoning is actually impacted by our hardwired physiology, and I'll actually go through that in the next slide. And then, obviously, we can't process big data sets unaided. And I use this perceptual example here. Of course, this is a pretty basic visual illusion. The lines are actually all the same length, but we cannot trick our visual systems into seeing them as different because of the way we're literally wired, right? The other thing is that stress impacts decision making. And now, you have to imagine that I'm in the middle of a talk where I'm arguing for humans being in the loop, but I have to tell you, the sort of the detriments, right? So when things are going great, right, our frontal lobes are totally engaged. We're directing our emotions and our thoughts. We've got this under control. And as soon as we get under stress, two things happen, right? The first thing that happens is well, first of all, a redistribution of blood and other things throughout the brain. We actually, sort of withdraw some energy from the frontal lobe of our brain, which then reduces our decision-making capability. But the second thing that happens is essentially our lizard brain turns on, right? And our lizard brain thinks everything is a threat. And so what we end up doing is not only reducing our sort of thinking capability, but then we start interpreting things as more negative than they actually are, which is like a really bad feedback loop to be in. So I just wanted to give you a context for, we've heard today, I think, some of the challenges that computers have, but also some of the challenges that humans have, and why we should actually combine them together. So I think we should combine them together because it's the places where, we talked about chess, right? And I don't necessarily want to go through that example again because we've talked about it, but in the case where the answer is not a one answer, right? There's no right answer. In chess, the moves are complex, but the outcome is sort of a known outcome, right? When we start talking about intelligence analysis, when we start talking about finance, decision-making, things like that, there really isn't one clear answer. And I think in those spaces, that's where we've really seen the combination of these systems coming together and giving us better results with the humans and machines combined together. I'm giving one example here, which I call sort of maritime domain awareness. So think about tracking bad guys on the oceans, piracy ships, people who have illegal arms and other things like that, right? A human cannot track, by itself, one vessel traveling through the oceans plus, the beacon information that's either present or not, plus the financial transactions that go from port to port as they move, plus, the satellite imagery. So we're now starting to see intelligence analysts who are using these, I'll call them, whether they're AI-enabled or they're complex decision-making systems, to actually start building hypotheses about where these bad guys are, where they're going to end up, what they've been involved in doing, and so you can actually track them. The other thing that a computer can do, and we saw this example earlier in the morning with the medical example of looking at it was a bladder example, right, in real time where those probabilities were being generated as the physician was looking at those. It's the same kind of thing, right? The computer algorithms are now generating hotspots in real time so an analyst can sort of see those and sort those out. So I think that's a great example of where now we're seeing this augmentation of human analysis, intelligence. So I put in parentheses there how our Centaur works. Everybody's welcome to build their own Centaur, however they see fit. But we think that a great combination is really enhancing it in two ways. So when I've talked about the Centaur, right, I've talked about an AI system with a human, but we haven't really talked about how to get information in and out of that human, right? So starting with the AI, I think two things that are particularly important and needed as we move forward into this development. The one is the idea of intuitive interfaces, really having a conversation with the human, communicating with the human in a way that they are best suited and you can get the most information in. And I have a slide on that, which I'll talk about more. The human operator itself, right? I'm a neuroscientist, so I'm going to tell you that we can measure lots of information about the individual. We can not only measure the amount of stress or engagement or attention or workload that they're experiencing, but we can actually measure very specific brain signals that are associated with particular pieces of information that are surfaced to them. And I'll also have a slide on that. So when we talked about the AI systems and engines, again, we're talking about something that's going to augment and not replace human intelligence. I'm actually good friends with the program manager at DARPA, Dave Gunning, who's sort of working on the explainable AI system. I agree that someone said today it's really about surfacing what's going on in deep learning and making it understandable to humans, but I still think all the things that we're working on, AJ's example today of transparent AI is exactly the kind of thing that we're talking about. But I also think that when you think about where they got to in freestyle chess, right, it wasn't that they were just using one engine and sort of making advances in how they were going to play. They actually were playing with all of the programs at the same time and actually evaluating and looking at which one might have the best move. And so the human was not only involved in evaluating the moves, but figuring out what combination of data might best suit the problem set, I think this is an example of where, as we get to more sophisticated problems, having alternative sources of data and models that actually are influenced by the operator are something of interest. In the computer-to-human component, we've talked mostly, all the things that we've discussed today have been very much 2D graphs and things that we've seen. There's a whole, sort of plethora of ways that you can interact with a human, whether that's three-dimensional data or multi-dimensional data shown to the individual. Audio, we haven't even talked about the mechanisms that we can use to get into the human brain, haptic touch, even olfaction as an alternative source of data into the human. So I think these are things that we all need to think about when we think about how we're presenting data to individuals, because even presenting things too simply or without the complexity can actually bias the decision making. On the human-to-computer component, I've talked before about the neuroscience piece. We can measure EEG, we can measure heart rate, eye movements, the behavioral actions. These do not just have to be sensors that are pasted on the human, although I have a slight bias towards that. But we can sense attention and workload and stress and surprise, all of the things that I think would be valuable as we're starting to close the loop on the individual. So I'm going to give you an example. This is actually from one of my programs back when I was at DARPA. This is an example of satellite imagery analysis. And so what we were actually able to do was, so imagery analysts look at huge images, like thousands and thousands of pixels, and they're looking for very specific things in them. What we were able to do was break those huge images up, right, and present them to the analyst very quickly. We were recording their brain signal at the same time, and you could actually measure when a chip passed by less than a second, 500 milliseconds or faster, when a chip passed by that had a target of interest in it, they had a huge brain signal, especially an expert analyst, that you could then attach that signature to that chip. You could sort those out, right? So that not only was their analysis task faster, but then you could use the images that they selected as part of what could feed into the computer vision system. So the whole system got smarter, right? The brain that directed as to what was interesting. The computer vision system was learning from the human. So then we got into this virtuous cycle where then the computer vision system would start by giving the analyst the most interesting chips, right? Didn't even have to look at the bottom 50% of things, and you got into a very virtuous cycle. This is exciting because it's easy to tell an analyst to look for buildings or ships or cars or whatever, but it's hard for a computer vision system or another system to switch between those. So this is an important result, and for me, one of my first Centaurs that I built. The second example is less of a Centaur, but more about human optimization, which is another program at DARPA was looking at accelerated learning, experts versus novices. Turns out the brains of experts actually look different than the brains of novices, and you can use that information, those brain signals, in a neurofeedback paradigm to actually train people to get better at that particular task. This was in marksmanship, and so it's a very physical task, but the experts could put themselves into that zone, into that state at will. And you could essentially train novices to put themselves into that zone. So I think both from these perspectives, both in terms of individual signatures, as well as sort of these zones or states that people go into, a very important contribution of neuroscience into the Centaur, what I call conversation. I think we're going to have a panel just following this about this conversations with AI. But what I've hoped to sketch out for you today is a closed loop system where you're actually having a natural interaction and conversation. The system understands something about you. You're getting communicated to in a way that's very natural and perhaps even a higher bandwidth than what we're used to. And actually really sort of closing the loop in a way that really improves the performance. Again, I think we're talking about situations where it's not just a one single answer, but there's a variety. There's a new program, or actually an ongoing program, I should say, at DARPA called Communicating with Computers, where the challenge problem is actually a physical problem, right? Where I think, humans and computers are trying to move, solve a task or move blocks around together. So we're starting to get into this space, but it hasn't been combined, I think, with the larger loop of AI and where the human operator or state is. So just to finish, I wanted to talk about some application domains. Again, you're welcome to project into my Centaur sort of idea the things that you're most interested in. Certainly finance, I think, is actually, for a Centaur, is actually one of the places that we're most interested in developing it. We've actually had some conversations in that space, and I think there's some interest. Those two worlds haven't quite merged together yet, and so that's very interesting. Intelligence analysis, mission planning, healthcare we heard today, business itself. The Air Force is actually invested in a concept that they call the wingman, so sort of an assistant or a wingman flying along with you that has an AI capability. And then finally, I wanted to call out something that I heard this morning, and I think is really important, the discovery and creative tasks. And so I'd like to leave you with a quote from Garry Kasparov from his most recent book, Deep Thinking. It says, intelligent machines will continue that process. Essentially, he's saying physical labor like now, right, physical labor was displaced, right? We don't pick cotton, he gave the example, he took us through time in that. Intelligent machines will continue the process, taking over more menial aspects of cognition and elevating our mental lives towards creativity, curiosity, beauty, and joy. I argue that as we move closer to these Centaur relationships and interactions, that what we're going to do is actually free ourselves up to have creative thoughts. If you read the book Where Good Ideas Come From, right, good ideas come from the pulling in of all these spaces and little intersections and things. It's not the people that were sort of super expert in this one domain that necessarily sort of sparked new ideas and new creativity. And so I might argue that while Centaurs will both make us better at the tasks that we sort of want to accomplish, I hope that they will also free up our creativity for beauty and joy and peace and all the things that I think we want to see for ourselves and for our families and children. So I thank you very much.